Question 3 from Paper 2 of the 2024 Higher Physics Examination from the SQA. A Newton's cradle is a popular desk ornament. The ball at the end is raised and then released, striking the closest of the four stationary balls. A force is transmitted through the stationary balls, which causes the ball at the opposite end to swing upwards. This ball then swings back and strikes the stationary balls from the opposite direction, and the process repeats. A physics teacher states a Newton's cradle can be used to demonstrate a number of physics principles, and for 3 marks we have to use our knowledge for this open question to comment on these statements. Well, let's take a look at how a Newton's cradle works. You can see we've got this situation here, all identical mass balls, and if you lift that one up at the end, this is this one here, if it's lifted up to the end and let go, you can see that the ball over here goes to almost the same height. Now, what principles is that showing? Well, first of all, it's coming down at a speed v, and the other ball is rising up to roughly the same height, so it must be leaving the speed v. So what we've got here is, first of all, a demonstration of the conservation of momentum. We can see that the first ball coming in, call it mass m, and has a certain speed v, and the ball leaving at the end will have a certain mass, same mass, and the same speed v. So we can show conservation of momentum. You can pick up 2 of those balls and let it drop, and 2 balls will go at the other side, once again emphasizing conservation of momentum. And the other one, which goes hand in hand to that, is the conservation of kinetic energy. And we can see that because the ball rises up to the same height, it must have the same speed here as the same speed initially this ball struck here with. So we can see we've got a conservation of kinetic energy. The collisions themselves, because the balls are made of steel, we can say that it's going to be an elastic collision. An elastic collision is when momentum and kinetic energy are conserved. And that's just because the actual physical structure of this ball is so hard that when something collides with it, it hardly deforms, and therefore it gives you that almost elastic collision. Now, we say momentum is transferred to each ball because if you look at the diagram, the first one strikes. If I go back up here and show this one, the first ball strikes here, and this ball hardly moves, but this ball transfers momentum to this ball here, shown you now, but it hardly moves, and because it can't move, it transfers momentum to the other ball, the green ball, and this green ball can't move because of its neighbour, and therefore it transmits its momentum to the other ball, the yellow ball, which can't move because of its neighbour here, but once it transfers momentum to this ball here, it can move the final red ball because it's not got a neighbour which to stop its motion. So there we can see momentum be transferred to each ball because they are stopped instantly by its neighbour until the last ball that cannot be stopped by its neighbour. And of course, this happens because the steel balls highly deform, and because they highly deform, you get this elastic collision. You can also use the fact that when you're lifting the first ball, you give it potential energy, and this potential energy is transferred into kinetic energy, and the speed of the ball does not depend on the mass of the ball, believe it or not, because if we've got the ball lifted up to a height, the first ball lifted up to a height of h, we calculate its potential energy to be mgh. Now, assuming that's all changed and transferred into kinetic energy at the bottom, would have Ek just before the ball strikes to be 1/2 mv squared. So therefore we must say these two are equal because if they're transferred, EP equals Ek, then we have mgh is going to equal to 1/2 mv squared. And you can put this in as well. You can see the two m's cancel, so you can make that a physics statement that the speed of the ball, if you rearrange, is going to be the square root of 2gh. Therefore you can say that the speed of the ball when it strikes the first ball in Newton's cradle doesn't depend on the velocity, doesn't depend on the mass, it just depends on how high you lift that ball up, and you can see that from the diagram there. Now, Newton's cradle, here we go, it lifts up, momentum is transferred all the way through the balls here like that until it gets to this last ball, and momentum finally is transferred to red ball, and therefore that moves up because there's no other neighbouring to hold it in place. So these are the things you can bring out in this situation here. You can bring out all the fact that you've got conservation of momentum, you've conservation of kinetic energy, and the very fact that it's only one ball that lifts up and strikes, and it'll mean one ball the other side will rise up. This is due to the constraints of the conservation of momentum and conservation of kinetic energy. That will only allow one ball to strike and one ball to lift up. Two balls to strike, two balls to lift up. Now that is very important when we think that we can also quote another thing, that the Newton's cradle, the masses of the ball must always be the same. Because if they're not the same, and I'll take you to another simulation here, you can see this simulation taking place. These balls have got different masses. This one's got 2 kilograms, 1 kilogram, 1.8. But watch what happens now when I lift the ball up. Will it lift the faraway ball up? Yeah, it does, but they all move, because once again it's this conservation of momentum. You get different masses involved here and it won't lift up. So you could maybe mention something like that. But once again, the only way you could actually write about that is if you played with a Newton cradle, and it's one of the most fantastic physics toys out. So that's a few ideas for this open question. Don't get into too many details. It's an open question, so you just got to take your time and just say conservation of momentum is illustrated, conservation of kinetic energy is illustrated as well. You're seeing an elastic collision taking place where momentum and kinetic energy are conserved. That's another good physics statement. And you also mentioned that momentum is transferred to each ball because they are stopped instantly by its neighbour until the last ball that can't be stopped by the neighbour, and therefore all that momentum is transferred to it. Lifting the first ball gives it potential energy. You can mention that. This potential energy is transferred into kinetic energy, and the speed of the ball doesn't depend on its mass at collision because of that little equation there you put in. EP equals mgh, ek equals a half mv squared, and of course you can see from this equation here that the speed at impact doesn't depend at all on the mass, only on the height. You could, if you were brave enough or had more experience enough with Newton's cradle, put in the fact that if the balls were different masses you wouldn't get that nice effect as you saw there, all because you have to have conservation momentum and conservation of kinetic energy for a pure elastic collision. One other thing you could actually comment on just before we leave this question is the fact that after a while things come to a rest, and that's because you're living in not a perfect world. You're living in the fact that each collision you're going to be losing a tiny amount of energy. You're going to be losing a tiny amount of energy on the actual strings due to friction and heat because they're moving, and eventually that small amounts of energy will take away from the real energy there, and the result of that, the system will come to a stop because there'll be no kinetic energy left. It'll be transferred into heat. So these are the things you could argue with that one in this open question.